Here is the question from a solid state class 12 standard. So what is the question? A compound form hexagonal closed spec structure. What is the total number of voids in 0.5 moles of it, and how many of these are tetrahedral voids here? So here is the solution. Look at here. Answer. So this compound, okay, this compound form hexagonal closed spec structure. So this hexagonal closed spec structure, let us write HCP. Now here, okay. So in terms of moles. So here in the compound the atoms present, okay. So it may be 2 or it may be 3, but here in the compound, so the atoms so arrange in HCP, okay. Suppose these atoms arrange in HCP, okay. How is the HCP? Just I show you. This is the, suppose the atoms, okay. These are the atoms. So 1, 2, 3, 4, 5, 6. So these 6 atoms surrounded the one of the atoms which I marked as close, and above this scale layer 3 more spheres there and 3 more spheres below it. Now here, so this is the small hole, this is the empty space left in between these k atoms. This empty space what we call, okay, voids. So according to the number of the k atoms, the type of the voids k, we have number 1 octahedral void and number 2 tetrahedral void. Now here, okay, so let us k in terms of the mole, let us suppose the number of atom in this HCP. So let us write K, 1 mole. So in 1 mole of the K atoms, K, how many atoms are there? Let me write here. Number of atoms in 1 mole. So that's the number we know, 6.022 into 10 to the power 23. That's the number of atoms. So this 6.022 into 10 to the power 23, that is what we call Avogadro's number. Okay. Now Avogadro's number is the number, okay, containing in 1 mole. Now here, if you know the number of atoms in K at HCP, so that number, so we just have a formula, number of the octahedral void. So here is also 6.022 into 10 to the power 23. Okay. And now number of tetrahedral void also here. So 2 into 6.022 into 10 to the power 23. So this is the case, okay, in 1 mole. Okay. Now our question is the total number of the voids in 0.5 mole. So now here let us calculate. Number 1, number of atoms in 1 mole is equal to, as I write here, 6.022 into 10 to the power 23 atoms. So from the data given, now here we are going to find out here number of atoms in 0.5 mole. So how do we calculate? 6.022 into 10 to the power 23 divided by 1 mole. Now this is the number of atoms, and multiply by 0.5 mole. So this mole can be cancelled. Now we do multiply 6.022 into 10 to the power 23 multiply by 0.5 atoms. Now here, when we do the calculation, when we multiply here 3.011 into 10 to the power 23 atoms. Now here, this is the number of atoms in 0.5 moles. Here the number 3.011 into 10 to the power 23. From that number, from the formulas given here. So what is the number of octahedral void? Number of octahedral void in 0.5 mole, that is same with this number 3.011 into 10 to the power 23 atoms. Similarly, let me calculate the number of tetrahedral void. Number of tetrahedral voids in 0.5 mole. So now here already we know this is the twice the octahedral void. So here we multiply 2 into 3.011 into 10 to the power 23. Not atom, this is the void, sorry. This is the void and this also void. How many voids here? 2 multiplied here, that is 6.022 into 10 to the power 23 voids. This is the number of the tetrahedral voids. Okay. Now here our question is, what is the total number of the voids? So in our close taking we have two types of the void. One is the octahedral void, another is the tetrahedral void here. So total number, therefore total number of voids, so in 0.5 mole, that is number of octahedral voids plus number of tetrahedral voids. Now here how many? So for the octahedral 3.011 into 10 to the power 23 plus, so what is the number of tetrahedral void? That is 6.022 into 10 to the power 23. So now here when we do the sum, addition, so that is 9.033 into 10 to the power 23 voids. This much number is present. Now second answer, so that second answer is from the tip. Here is the answer. So number of the tetrahedral voids in 0.5 mole. That's already we calculate. That is 6.022 into 10 to the power 23 void. This is the answer, for that question. To remember, So this questions from the solid state. So this is the question from the in-text exercise. So you remember, that's very important, and based on the logic. Here is another question. It's the same with the previous question. Only the difference is, so here, let me read the question. A compound is formed by the cation C and anion A. Now here the anion forms hexagonal closed stacking lattice. Instead we used to say HCP. And the cations, what the cations A, so that's so anion already, right? Cation C occupied 75% of the octahedral void. Now here the question is the formula of the compound. See here, let me give it again, simple hints here. So in the hexagonal closed stack structure, as I show you, this is the atoms. Now here, 6 another atoms is surrounded, in the same layer, 1, 2, 3, 4, 5, another 6 spheres, and above this layer 3 more spheres above it, and 3 more spheres in just below it, right? Now here, so the empty space left in between these closely packed K atoms, this empty space what we normally call void. So this voids, okay, in the closed packed K structure, so two types of the voids are present. One is the octahedral void, another is tetrahedral void. Now in the question here, that is only the octahedral void, right? Now, if you know the number of these K atoms, if you know the number of the atoms present in the K octahedral void, so we could find out what is the number of them. Then after that we can write their K molecular or empirical formula. So how we will calculate? So options are given here. Options are just given here that we find out what will be the answer of them. Now here, see, since so the anions, what the anions here, that is written here A. So what types of the closed packing it form okay, high CP. So if this A form the high CP, that means the bigger circles which drawn here, that is represented for the anion. So now we can suppose a number. Okay, instead to write suppose, so the percentage is given here in percentage. So now let me write number of anion A, that is out of this 100%, that is 100. So out of the 100, okay, 75% of the octahedral void is occupied. So let me write from this number of octahedral voids, that is same with the number of the anion here, that is 100. So now, so the cations, okay, how much percent is occupied here? Cations, okay. So cations, what the cations written here? C. That occupied how much percentage? 75% of octahedral voids. That means how many number of the cations? C, that is equal to 75. Okay, so percentage, that is 75, right? So this is the number of the 100, so we can write 100. So that is this is the 100. Is it correct? Now here, so without 100 we can write the 75. So now if we know that this number of the cations, if you know the number of the anions here, so we can write the ratio. What is the ratio of this? Ratio of, so normally cations we write it first and the anions followed by anions. So what is the ratio? So that is the number of cations 75 is to the number of the anion is 100. So now we can convert it into the simplest whole number ratio by dividing the 25. When we divided 25, so that is come out so it should be 3:4. If you know that this ratio, so we can find out the formula. What it should be the formula? Formula of this compound. What would be the formula? So number of the C, here is the 3, number of the A is here is the 4. So what is the formula? C 3 A 4. This is the formula. So now here, what is the option? Option number 3 is correct answer. Right. So you just remember it. Okay. So here is the another question. Okay, this is from the solid state. Now here, what the question is, an element has BCC. What is the full form of the BCC? Body center closed packing structure. So with a cell is of 288 picometer. Now here, what is cell A? Still look at this. This is the one of the unit cell. So here, this length of this side, this length of this side and this length of this side, what we call cell A, or we can say S length. What is cell KS? We write here A. Okay. So now this is the cell is, what we write it A, and this is another cell is, what we write it A, and this is another. All these sides are same, so I write all are A. Now here in BCC, what the BCC means, okay, body center close packing, so constituents, I mean the elements are all occupied at corners. How many corners are there? 8 corners. So I don't draw it here, so you please remember key elements are present at all the corners, right? Then now one more key elements present at the center of this body. Where is the center? So I just pointed here. This is the center of this box. Now here one of the atoms is written, I think is occupied here. One of the atoms is also occupied here at this corner, and one of the atoms at the center of this body, right? But I just keep some distance, but all these three spheres are connected to each other. That's I wrote here, right? So this AD, which I write here, one sphere, I mean one elements I drawn here, another element at the body center, just I drew here, another element. So this is the AD. What is the AD? So this is the AD means body diagonal. So this corner and opposite of this corner here. So the line passing through this center of the body, that's the line what we call body diagonal. Now what is the body diagonal? I just write AD. So now how long AD? So there are 3 circles which I drawn here. One of the radius of this circle, and there are 2 radius of this circle, and one more radius here. How many are here? 4 are. So 4 are is the distance of the body diagonal. Now, okay. Then now, so here the question is the cell is and the radius of the atom. So now let me find our radius. See here the radius is 4r. Now where is the S length? So for the body diagonal, what is the cell? I mean what is the body diagonal? That is the root 3e. How we could find out this root 3e? Just I show you. Now here we have a 2 triangle. One is here, another is here. So for this triangle ABC, so by Pythagoras theorem, AB square, that means AB square, this AB, that is the first diagonal. AB square is equal to AC square, the square of the one side plus square of the another side, that is the BC square. What is the length of the AC? As I said before, this is the length of this side A. So A square plus A square, that means twice A square. AB square means twice A square. Then now another triangle is ABD. That is, I just show you this triangle ABD. So by Pythagoras theorem, AD means body diagonal, square, that is the square of the one side, that is the AB square, plus BD square, that is another side. So what is the length of the AB square? That is the twice A square. And what is the BD? That is the length of this side A. So that is the A square. Then now sum of these two, that is the 3A square. Now we are going to find out the AD. AD means so root over 3A square. So this square, this root can be cancelled, and now it's remain root 3A. So that means AD means body diagonal is equal to root 3A. So here the AD also root 3A, here AD also 4R. So that means the relation between this, so 4R is equal to root 3A. Now we are going to calculate this R. R is equal to root 3 divided by 4 into A. Now, so what is the value of A here? A value is 288 picometer. So now instead of this A substitute by 288 picometer. So this is the option where it's given here. So that option number 1 is the correct answer. So this is the relation between the cell S means S length and the radius of the element in the BCC structure. Okay, remember it.